Hello, welcome to my channel. In this EMF video, I'm gonna solve practice exercise problem on vector calculus from chapter 3 from the book Elements of Electromagnetics by Matthew Sadiko. And we have to find here in this problem, we have to find the circulation of this vector around this edge defined by this, and we have to verify the answer by Stokes theorem. So let's get started. So before we get to the problem solving part, I'm gonna try to discuss about Stokes theorem. What is this? What is Stokes theorem? So let's get to that first. In the previous video I discussed about curl of a vector. So curl of a vector is a vector which measures the maximum circulation of a vector per unit area, and the direction of the circulation is normal to the surface of the circulation. So curl of a vector has its corresponding theorem called Stokes theorem. It states that given a vector field A, if there is a circulation of a vector around a closed path on a surface, we can express that circulation around closed path by surface integral of the curl of the vector. So this is the Stokes theorem. Line integral of the vector around closed path is the same as surface integral of the curl of that vector. So this is the Stokes theorem, and we're going to apply it to verify our result for the practice exercise problem. So first let us find the circulation. So circulation means closed path. So the closed path ADL is, so let us first divide this in three parts. So the line along x-axis, so which is so 1, which is along x-axis, a dl plus the second path, which is an arc, this a dl plus this is along x and y, so row along row path row, so which is 3, so ADL. So this is, so differential length in cylindrical coordinate system is d rho a rho. So along path 1, so path 1 ADL is, so 0 to 2 rho cos phi d rho, which is cos phi rho square by 2, 0 to 2, which is, so cos phi, so phi here is 0, so cos 0 dot half 2 square, which is 4 by 2 is 2. Now along path 2 differential length, along path 2 differential length is, we can see that this is rotating, it's an arc, so the path is an arc, so it is rho d phi in the direction a phi. Now along path 2 ADL. So there is no phi component i- in the direction phi for the vector, so this is 0 to pi by 360 degree in radian, and as there is no phi component, so this is this and rho d phi, which is 0. Now along path 3, differential length is, so rho a rho. So along this path 3, the differential length is also d rho in the direction arrow differential length. So ADL is, so this is 2 to 0 rho cos phi d rho. So this is scalar multiple, so only arrow part will be here and no z part because they are perpendicular to each other. Now but so cos 60, so here is cos 60 in this case, and there is obviously half rho square 2 to 0, so which is, so this will give us -1. So now what we're gonna do is we're gonna verify the result of the circulation we found by Stokes theorem. So before that we're gonna take the curl of this vector. So curl, so vector multiplication, so this is incidentally, so 1 by rho a rho a phi a z, partial differentiation and partial differentiation, and a rho is rho cos phi 0, there's no phi component, and z sin phi, so this will give us 1 by rho partial differentiation with respect to phi z sin phi minus 0 a rho minus partial differentiation with respect to rho z sin phi minus partial differentiation with respect to z rho cos phi rho a phi plus, so z is 0 minus partial differentiation with respect to phi rho cos phi az. This will give us, so here this whole term is 0, so 0 a phi, and here minus plus rho sin phi az, which will give us z by rho cos phi a rho plus sin phi az. So this is the curl of this vector. So now by Stokes theorem, so line integral along closed path can be represented by surface integral of the curl of the vector. So ds. So we have found curl, so we have found line integral. Now we're gonna analyze the surface integral now. So here differential surface is rho d phi in the direction az. The surface integral curl of the vector ds is 0 to 2 rho and 0 to pi by 3, so rho and phi, and the component, so z component of the uh, curl is sine phi, and rho d phi. So we found our curl, which is z by rho cos phi a rho plus sin phi az. So this is our surface integral now. So this now rho square 0 to 2 minus cos phi 0 to pi by 3 is and thus after the calculation we have found our answer 1, thus verified. So this is equal to the line integral we previously we found, so this is verified. So we have verified by the Stokes theorem that line integral of a vector along closed path is the same as surface integral of the curl of that vector. So that's it. Thank you for watching this far. I hope you understood my explanation, and thank you very much.